Seasonality, sometimes referred to as seasonal variation, is a common phenomenon in time series variables. It is a situation where the time series variable changes in a predictable pattern that keeps repeating over time. For instance, consider the behavior of the tourism industry of a hill station. It will see a rise in tourism during the summer months and a subsequent fall during winter. In other words, tourism activity in a hill station will be high during summers and low during winters. This seasonal variation is repeated each year, showing a wave-like pattern in the time series. If we take a look at the graph here, it shows a clear seasonal pattern that is repeating every year. We can see consistent peaks and troughs in the time series that are repeating or recurring every year. Moreover, the pattern of seasonality usually depends on the type of data. If we are dealing with monthly data like in the graph shown here, the seasonal pattern repeats every 12 time periods. Similarly, the seasonal pattern repeats every 4 time periods in quarterly data. The seasonality or seasonal behavior of a time series variable may be either additive or multiplicative in nature. It is essential to distinguish between the two because they need to be handled differently. Additive seasonality is a situation where the magnitude of the pattern remains the same with time, trend, or changing mean. With the passage of time, changes in mean or the falling or rising of trend in the variable, the magnitude of the seasonal pattern does not change. This means that the height of the peaks and the depth of the troughs remain more or less the same. The first graph shown here is a good example of additive seasonality because the magnitude of the pattern is the same over time or trend. Multiplicative seasonality refers to the seasonal behavior that changes its magnitude with time, mean, or trend. With an increase in the trend or mean, the magnitude of the seasonal pattern also increases. Conversely, the magnitude of seasonal variation falls with a falling trend or mean. This implies that as the mean or trend increases, the peaks in the seasonal pattern become higher and the troughs become deeper. This is clearly visible in the second graph shown here as the magnitude of the pattern is increasing with the trend. Additive seasonality may be modeled within the ARIMA framework using AR and MA terms. However, we need to use the SARIMA models in the case of multiplicative seasonality. In both cases, it is generally advised to consider the SARIMA and multiplicative model first and check how it is performing as compared to the ARIMA model. Additive seasonality can be accounted for within the ARIMA models. Using AR terms, MA terms, or seasonal difference is usually enough when dealing with additive seasonality. In the equation shown here, D is the order of integration or differencing as usual. We also have one lag of AR and one lag of MA terms in this ARIMA equation. The interesting part here is the seasonal lags of AR and MA terms. Here, S refers to the length of the seasonal period. For example, this S will be 12 in case of monthly data and 4 in case of quarterly data. The AR term of YT-S is the seasonal AR term in this equation and alpha S is the coefficient of this seasonal AR term. Similarly, mu-T-S is the seasonal MA term in this equation and theta S is its coefficient. We refer to this as additive seasonality because the seasonal AR, MA terms and their coefficients are entered as additions in the equation. Suppose that we have quarterly data and an ARIMA 1-1-1 model. If we decide to include one AR and one MA additive seasonal lag, then our ARIMA equation would be similar to the one shown here. Delta YT means the first difference of YT, and this is a non-seasonal difference. The AR1 and MA1 lags are the same as in the usual ARIMA 1-1-1 model. The term delta YT-4 is the seasonal AR lag and mu-T-4 is the seasonal MA lag. Both these terms are additive AR and MA lags because they are simply added to the other terms in the equation. Moreover, S is equal to 4 and we are using T minus for lag in seasonal ARIMA terms because we are considering quarterly data. This ARIMA model can be easily expressed in lag operator notations as shown here. Again, we can see here that the seasonal AR and MA terms are additive in nature here. The first ARIMA equation shown here is the example of additive seasonality we considered earlier. The seasonal AR and MA terms are entered as additions to the other ARIMA lags. In case of multiplicative seasonality, we have to use the SARIMA model, which is specified as ARIMA rho, D, Q, SARIMA capital P, capital D, capital Q and S. The ARIMA terms rho, D and Q are the same as we discussed in the ARIMA models. The additional SARIMA terms represent the seasonal AR lags with capital P, seasonal MA lags with capital Q and seasonal differencing with capital D. The term S refers to the length of the seasonal period. Using lag operator notation, we can specify the basic form of SARIMA models as shown here. The important thing to note here is that the usual AR, MA terms and the seasonal AR, MA terms are not added to each other. Rather, they are specified as being multiplied by each other. The alpha SL raised to the power P represents the multiplicative seasonal AR terms and capital P is the order of seasonal AR lags. On the other hand, theta SL raised to the power Q represents the multiplicative seasonal MA terms and capital Q is the order of seasonal MA lags. To make the SARIMA specification clear, let us consider an example of a simple SARIMA model. Here, we can see what the equation for seasonal ARIMA or SARIMA 1 by 1, 12 model will look like in practice. The seasonal period S is equal to 12 in this example, which implies that we are dealing with monthly data. The order of seasonal difference or capital D is equal to 1. This means that we have to take the first seasonal difference of the variable. Since we are using monthly data with S equals 12, delta 12 YT signifies the first seasonal difference and it will be equal to YT minus 12. In addition to this, we can see that the order of integration or lowercase d is also 1 in this model as shown by the ARIMA part. This means that we have to also take the first non-seasonal difference after taking the first seasonal difference of YT. Because rho is equal to 1, we have to include one non-seasonal AR term which is shown in red. Similarly, Q is equal to 1 and we have to include one non-seasonal MA term in the model which is shown in blue. These two terms in red and blue represent our non-seasonal ARIMA part of the model. The seasonal AR part of the model is shown in purple here. The order of seasonal AR terms is 1 in this example. Therefore, we only have one seasonal AR lag and its coefficient alpha 12. The second term shown here is the multiplicative part of seasonal AR term which represents the nature of multiplicative seasonality. This is because the AR coefficient alpha 1 and the seasonal AR coefficient alpha 12 are multiplied by each other here. Additionally, we can also observe that T-13 or 13th lag of the variable being used here. Similar to the seasonal AR term, we also have a seasonal MA part in the model. The order of seasonal MA term is 1 represented by capital Q. As a result, we have a seasonal MA lag and its coefficient theta 12. The second term here represents the multiplicative part as the coefficient theta 1 and theta 12 are multiplied by each other. We can also observe that the mu T-13 is attached to this term. This equation shows exactly how the seasonal AR, seasonal MA and seasonal difference are represented in the model along with the usual ARIMA terms. To estimate the SARIMA models, we must decide the order of seasonal and non-seasonal difference, AR and MA terms in the model. In addition to the usual AR and MA terms in the ARIMA model, we must also determine the order of capital P, D and Q for seasonal terms. In the previous tutorial, we used the ACF and PACF plots to determine the order of ARIMA models. we discussed different rules about the ACF and PACF that can be used to determine the order of ARIMA models. Those same rules are applicable to the seasonal difference, order of seasonal AR and seasonal MA terms. The only difference is that we now focus on the ACF and PACF lags at the length of the seasonal period. For example, let us say that we are dealing with quarterly data. Then, we will focus on ACF and PACF at lags 4, 8, 12, 16 and so on to decide the order of seasonal terms. That is, we use the same increment as the length of the seasonal period. First, let us take a look at a seasonal time series and its ACF plot. In the first plot, we can see that the series is not stationary as there is a clear indication of seasonality and the seasonal pattern is repeating every year. Moreover, it looks like the seasonality is multiplicative in nature. If we look at the ACF plot of the series, we can see a distinct wave-like pattern which is declining gradually. This wave-like pattern is an indication of seasonal behavior. Let us look at the ACF at first seasonal lag, which is ACF at lag 12 because this is monthly data and the seasonal period is equal to 12. We can observe that the ACF at the first seasonal lag or lag 12 is quite high, around 0.8. Also, the ACF at further seasonal lags of 24 and 36 are gradually declining. This indicates that we might need to take a seasonal difference of the series. In such a case, taking a usual non-seasonal difference like we did in ARIMA models will not be enough. If we take a non-seasonal difference, the plot of the series will look like the first graph shown here. This first non-seasonally differenced series is clearly not stationary. Moreover, we can see clear spikes in the ACF plot at each seasonal lag. Again, the ACF at lag 12 or the first seasonal lag is even higher than 0.8. All of this indicates that we should take a seasonal difference of the time series. Now, let us see how to decide the seasonal AR and seasonal MA terms in the SARIMA model. To illustrate this, we will consider the ACF and PACF of a quarterly time series. That is, the length of the seasonal period will be 4. The two graphs show the ACF and PACF plots which show a typical seasonal AR process. The rules for determining the seasonal AR process and lags are the same as the usual non-seasonal AR lags. The difference is that we now focus on the ACF at seasonal lags. In the ACF plot, we can see that the ACF at seasonal lags of 4, 8, 12 and 16 are declining gradually. On the other hand, the PACF at seasonal lags show a sharp cutoff after two seasonal periods of lag 4 and lag 8. This indicates that two seasonal AR lags will be a good starting point for the SARIMA model because the PACF shows a sharp cutoff after two significant seasonal lags. The next two plots of ACF and PACF show a typical seasonal MA process because the PACF is declining gradually at seasonal lags while the ACF shows a sharp cutoff after two seasonal lags at lag 4 and lag 8. This means that two seasonal MA lags is a good starting point for the SARIMA model because the ACF cuts off sharply after two seasonal lags. If both the ACF and PACF plots show a gradual decline after each seasonal lag and there is no clear cutoff in ACF or PACF, then we might be looking at a seasonal ARIMA process. In that case, we might have to include both seasonal AR and seasonal MA terms in the SARIMA model. Like in ARIMA models, we must be careful when including both seasonal AR and seasonal MA terms because they could possibly interfere with each other. Moreover, all the other things discussed in the ARIMA models that we must watch out for are also applicable to seasonal ARIMA terms. For example, we must watch out for seasonal overdifferencing just as we did in the usual ARIMA models. Another important thing to note in SARIMA models is that we should generally not use more than one seasonal difference or even more than one or two seasonal AR and MA terms. This is because one seasonal difference, one seasonal AR or one seasonal MA term is usually enough. Including more terms can lead to estimation problems. For instance, the model may not converge when we include too many seasonal terms. Moreover, too many seasonal terms can restrict the dataset being used for estimation. Thank you for watching, and I will see you in the next tutorial.